Okay, in this final part of the talk, I'll apply our controller design method for achieving temperature tracking in a rectangular room. And these simulations and the controller design were carried out by my PhD student Konsta Huhtala, and this is related to his thesis work, which is also joint work with Weiwei. So we have a rectangular space with some fluid in it, and we model the temperature profile of the fluid. The walls of the room have two openings, one on the left side with an inflow of the fluid, and another one on the right side with outflow of the fluid. And our aim is to achieve output tracking of the average temperature in this red square while controlling the temperature in this blue rectangle. And in addition, there is a temperature disturbance input at the boundary at the opening of the wall. And in this simulation example, it is assumed that the velocity of the fluid is all the time in its steady state. And in this case, the temperature can be modeled by a diffusion convection equation on the first line with the control input, and the velocity field V is determined by the incompressible steady-state Navier-Stokes equations on the second line. And finally, the temperature measurement is the average integral over the red square. And in this simulation example, our aim is to achieve output convergence to a reference signal with two sinusoidal components with frequencies 1 and 2, while at the same time rejecting the boundary disturbance with frequency 3. The reduced order controller design that Konsta carried out then is based on the three frequencies 1, 2 and 3, and the knowledge that our system has a single output Y. And the PDE model is approximated with the finite element method using quadratic basis functions, arriving at a fairly high order system. And as mentioned before, the controller design can be implemented using MATLAB built-in functions, and what we end up with is a robust controller with total dimension 16, consisting of the dimension of the internal model plus the remaining parts with dimension R. And on this slide we plot the output of the system as well as a snapshot of the temperature profile, and what we can observe is nice convergence of the output to the reference signal. And finally, I'll show an animation of the evolution of the controlled temperature profile. And the temperature profile is shown on the left here. The inlet and the place of the control input are shown at the front of the figure. The red dots inside the spatial domain denote the area where the temperature measurement is taken. And on the right hand side here, you can see the evolution of the temperature measurement as well as the tracking error. Finally, to summarize, in this presentation I've introduced a new low-order robust controller design method for output regulation of parabolic systems, and this controller design is based on Galerkin approximations, and it is quite straightforward and easily implementable, for example using the built-in MATLAB routines for linear quadratic design and model reduction. And here I'm also listing few of the references on which this talk is based on. The first one being our main paper on this topic, and the second one presenting extensions of the results for boundary controlled PDEs. And the simulation examples are taken from Konsta's paper at the MTNS conference this year. And finally, I want to also mention that the controller is also implemented in our group's software package ROARpack, which is now coming out as a MATLAB version, and it previously existed as a Python library.